Unit 5.9, Transforming Polynomial Functions. In this unit, we're going to apply transformation to graphs of polynomials. So we know there are only 4 types of transformations in the graph. The first one, we have translate up or down, and then we have shift to the left or right, and then we have vertically stretched or compressed, and the last one we have the reflection across the x-axis. So that it all go back to that basic absolute value functions formula or standard form like this. And all these variables a, h, and k, as well as the sign before the value of a, determines all this transformation. So the sign before a, if it's negative, we have reflection across the x-axis. For a, if the value of a or absolute value of a is bigger than 0, we have vertically stretch. And if it's between the value of 0 and 1, we have vertically compressed. And for h, the value of h control the shift to the left or right, and k control the movement of translate up or down. We can apply the same thing from this standard form of the absolute value function in the graphing of polynomials as well. Here's an example. You're asked to sketch the graph of this function. The first thing you know right away, it is a cubic function, because the biggest power of the function is 3. And since it's a cubic function, you know the parent functions is going to be like this. This is the parent function of a cubic polynomial, which is y equal to x cubed. The next things I'm going to do is to line this up with the basic form of an absolute value function. We know all these variables, and the sign before a control all kinds of transformation. In this case, the sign before a is negative, so we know there's going to be a reflection across x-axis. So the reflection across x-axis on the left part is going to be like this, and the right part is going to be like this. So here we got y equal to negative x cubed. This is a reflection across the x-axis. The next things I'm going to look at is the value of a. Since a is equal to half and it is less than 1 and bigger than 0, we know it's going to be a vertically compressed transformations. So it's going to be flatter like this. So this one is y equal to negative half x to the third power. The next thing we look at is the h value, which is 3. So h equal to 3. We know it's going to be shift to the right by 3 units. So we just count 1, 2, 3. So the graph's gonna be like this. This one is equal to y equal to negative 1/2 x minus 3 to the whole square. The last movement is the k, which is plus 2. Plus 2 means you're going to translate out by 2. So the final movement here is translate up by 2. So say 1, 2 right here. So the graph end up is going to be right here. So this is the point 3 and 2. So we have y equal to negative half x minus 3 whole square plus 2. So this is the final destination after all the 4 types of transformation. The last concept that we are going to learn in this unit is power function. The power function is in the form of y equal to a times x to the b power. A, sometimes known as the scaling factor, which control the transformation of vertically compressed or stretched. The sign before this scaling factor A control the reflection across the x-axis. So for example, in this one, 0.5, since it's less than 1 and bigger than 0, so we know it's going to be a vertically compressed one. And the sign before it is positive, so there's no reflection across the x-axis. For this one, since A, 4 here is bigger than 1, 4 is bigger than 1, so it is a vertically stretched. And because the sign is negative before the scaling factor right here, so there's a reflection across the x-axis. The next concept that we have to learn in the power function is constant of proportionality. What it means is when you have a power function like this, it basically means y varies directly with or proportional to the b power of x. We actually learned this before in chapter 2. In chapter 2, we learned the concept of y equal to kx, k times x, and we call k as constant of variation. And we can also say y varies directly with x. So the only difference when you compare this one to y equal to a x to the b power is that in constant of variation, the power of x is 1, while in the power function, b is a positive number. It could be an integer or it can be a fraction. And in both concepts, y is proportional to x. In the next slide, I'm going to show you an example. In this example, it's going to show you how the concept of power function apply in a real-world context. So let's translate the words in the problems into a mathematical model first. So some key facts here are, first, the power p, which is a variable, varies directly as the cube of the wind speed v, which is another variable. Based on this sentence, we can already translate it to p equal to a times v to the cube, because it is a direct variations relationship. Now the question is, how much power does this turbine can generate in a 10 miles per second wind? Since we have this direct variation right there, and they give you a data which is when the wind is 8 miles per second, it could generate that much of power. So we set it up as the equation right there, which is a power function. Then we just solve for A. Once we find A, we can plug it back into the original equation, which is a power function again, and then solve for P when V equals to 10. Then here's the answer.